second unit on calculus is how can we use all the information about derivatives to help us with other stuff, applying it. And application number one that we're going to do is curve sketching, also known as graphing, also known as your favorite unit from grade 12, the 5 units on graphing. You were like, yay, we get a graph. So, what do we do? How do we use this to help us? Because you have learned graphing in the past. You could graph this parabola. Maybe you remember some of the techniques you did to graph parabolas when they were like this. Remember any techniques? Or even what they were called? Or even the basic idea? What would you do?
Find the intercept.
You could find the intercepts. We could find the x-intercept and y-intercept, and you could do those by plugging in zeros. You could use transformations, but in this form, you couldn't do the transformations. You remember that you had to sort of have it. Did you use P and Q or H and K? H and K? Some textbooks use P and Q, some use H and K. This is called the vertex form. What was really nice about this form is that you knew that, and from transformations as well, this would move it P units left or right, Q units up or down, and then you could find the vertex that way. Your vertex would be P comma Q. So in grade 11, you learned a technique called completing the square to do this. Do you remember the completing the square technique? Where first, if you wanted it to look like this, you said, well, there's an A value factored out, so I'm going to take the 3 out of the first two terms. I'm going to leave the -1 because that's probably part of the cube. And this is what I would have. Now I need this part here in the brackets to eventually become something squared. And in order to make that something squared, this was a hint. What's the only binomial squared that gives you a +4? Is if you had +2, x plus 2 times x plus 2. When you multiply that out, well, you could get a 4x. Then, but if I do that, I would also get a number here. So in the completing the square technique, your teacher might have said, we're going to put a space here, and we're also going to put a space here. Because if I add, what's needed to get this +2 is adding 4, but I can't just add 4 to one side of the equation, it makes it lopsided. So I should subtract 4 to make it balance. But I haven't actually I have to subtract 12, because that 4 was actually also then multiplied by this 3. And then I actually added 12, so to compensate I needed to subtract 12, which would give me -13 here, and I now know my vertex is at -2, 13. Introduce you to calculus and the derivative. What does the derivative do? The derivative finds the slope of a tangent line all around the curve. This is a parabola that opens up. The key point in graphing a parabola is the vertex, sommet in French, right? Remember that word? Okay. And if I find that vertex, it's kind of important. We found it with completing the square. How does the derivative help us? Well, the derivative finds the slope of any tangent at any point. And at the vertex, the tangent line is perfectly flat. In other words, the tangent line will be 0 at a maximum or a minimum because of that. This will be the key application technique for graphing using derivatives. Because how hard is it to find the derivative of our function? Super simple. Would you agree that y prime would be 6x plus 12? And if the slope is 0, meaning you could plug in 0 for the slope, how hard would it be for you to figure out that the x value has to be -2? Quicker than completing the square? Yes. And if I wanted to find the y coordinate, well then I could just go back to my original equation, plug in -2. I would get 12 minus 24 minus 1. And I would get my vertex that quick. This is the frustrating thing about math, is that as you learn more complicated math, you realize that the complicated math you learned before, you now know easier ways to do it. You're like, why didn't they just teach us the easy ways first? Because you couldn't understand the easy ways unless you understand the complicated stuff that comes before it. But now, we can graph our parabola that much easier. Awesome. So, we do an analysis of what we have happening with our derivatives. If the derivative is equal to 0, that means you have a tangent line that is flat. When do you have tangent lines that are flat on a graph? If I pick some cubic graph here, I would have a flat one there and a flat one there. So our derivative, if we set it equal to 0, is a quick way to find any maximum and any minimum on a graph. If you remember graphing things like this last year in grade 12, you found x-intercepts, you found the end behavior, you got the shape, and the one thing that your teacher might have said is, we're just going to have to estimate where the maximums and minimums are because we don't have the mathematics to find it easily yet. And the mathematics to find those maximums and minimums is actually, once you know derivatives, extremely simple. Because the tangents will always be 0, horizontal, at those points. Now, if your derivative is greater than 0, that would mean you have positive slopes. I'm going to switch colors. I'm going to do this, because I'm going to use my same example that I had before. It's getting a little intense. Our slopes would be positive. Can you see where you could draw tangents on our original graph where the slopes are positives? That will be, like, I could do one here, right? Or here, it would be a positive slope, or here, or here, or here. We would say in that section, our graph is increasing. And if our slopes are negative, and I look anywhere on our graph where I can draw tangents with a negative slope, can you see where I put those red dots? That the graph is going down from left to right. So we would say graph is decreasing. Now going back to our parabola that we just did. Sorry, I went kind of quick there. Is everybody done? Probably not. I will wait. Are we good? So if we go back to our parabola, now, since you know stuff about parabolas, once you found your vertex, you would know that it goes up because the a value is positive. That's something that you've learned in grade 11. You know, some parabolas go up, some parabolas go down. It's all based on what's in front of the x squared. We had a 3 in front of the x squared, which is positive. Ours is going up. But what we're going to find out in calculus is once we find out that -2 was our vertex, our minimum or maximum point, we are going to draw a number line with -2, and then we're going to check what happens in each of these sections. So for example, when you check your derivative of something less than -2, I'll write it like that. If I plug in any number less than -2 into my derivative, like -3, do I get a positive or a negative number? If I plug in -3, -18 plus 12 will be -6. In fact, anything in this section that you plug in will give you a negative number, which tells you your slopes are negative. If your slopes are negative, your graph will be decreasing. If I plug anything bigger than 2, if I plug in something for x, that x is bigger than 2, x is bigger than 2, I kind of wrote this. This, I just plugged in something for f of x where x was less than 2. Now I'm going to look at f prime of x if x is bigger than 2. If I plugged in 5, 6 times 5 plus 12, positive number, which means that our graph is increasing. Do you see that in your parabola? You've got your vertex. It's decreasing, then increasing. That's what a parabola does. Now we knew that already, but this is going to help us for calculus, because we might have graphs that we don't know which way it's going. And we'll be able to figure that out. Or maybe you forgot how to graph an x to the 5 graph from grade 12 last year. This is going to help figure it out. It will create an easy way for us to graph. So part 1, looking at increasing and decreasing. We say something's increasing if it's going up from left to right. We say something is decreasing if it's going down from left to right. So if we look at this graph, in purple, I'm going to label I have a maximum point there and a minimum point there. Increasing, I'm going to show in green. Can you see the graph is increasing here and increasing here, but the graph is decreasing in red here. And if at any one of those green points I drew a tangent, that tangent would have a positive slope. At any one of the red points, if I drew a tangent line, can you see that that tangent would have a negative slope? So it allows us to figure out that if you find a section where your derivative is always negative, your actual graph will always be decreasing in that section. And if you find a section that's always positive, your graph will always be increasing. So it's going to be important for us to find out where it is 0, because when your slope is 0, that's the only place it could possibly change from being positive to negative. If your number is changing from positive to negative, you would need to have a 0 in between. So we label the increasing, we color code this in green, and the decreasing, color coded that in red. Sometimes we use the word gradient for slope, right? You draw a tangent where it's increasing, you'll have a positive slope. And if the slope is positive, that means your derivative would be positive, because all your derivative is doing is finding slopes of tangents. If your slope is negative, that means your derivative is negative. So how do we find the sections that are increasing and decreasing using calculus? Well, this is a parabola, okay? The parabola is going to be decreasing till it hits the vertex, and then it's going to be increasing afterwards. And would you agree that this parabola is opening up? So if we found this vertex, we'd be able to say that what's on the left is decreasing, what's on the right is increasing. How do we show that same thing using calculus? We find the derivative. Super easy. 4x plus 1. We need to find out where that derivative, if the slope is 0 is where the vertex will be, I can just plug in 0 for the derivative and say, oh, that is going to happen when x is negative 1/4. So I now imagine a number line with negative 1/4. And I can plug in numbers less. Sometimes what I do on this number line is I write f prime of x beside it to remind myself, if I want to find out where it's increasing, decreasing, I'm going to plug in values into the derivative, not into the original function. So now, what's going to happen that sometimes gets confusing, we are going to usually have 3 equations. A regular equation, a first derivative equation, and a second derivative equation. And when you plug something into them, they all tell you different things. So when you want to find something out, you need to know which one you're plugging it into. To find out where your graph is increasing and decreasing is based on the slopes of the tangent, so we need to plug things in to the derivative. So I write a little derivative here saying, I'm going to plug in something less than negative 1/4 into my derivative, like negative 2. And I don't care that the answer is negative 7, right? Unless I'm like, I really want to practice my mental math. But all I care about is it going to be positive or negative? I can see in this section, when I plug in negative 2, I'm going to get a negative answer, which means, and I like to draw it this way, my graph is decreasing. And that matches up with the red part of our parabola, which we know. Going from left to right, it's decreasing. We're not thinking right to left. The arrowhead makes it, oh, it keeps going up though. But if I'm moving from left to right, if I took a little point, oh boy, here we go. If we took a little point on our graph and had it travel along the red one, that little point moving from left to right would be decreasing. Okay? And if we check something bigger than negative 1/4, like 0, 0, very easy mental math to plug in, you'll get positive 1. All I need to know is that this section is positive, and that would be going up. And sure enough, if you went from left to right from the vertex, things would be looking better. You'd be going up. It'd be almost the weekend. All good. So many positive, you could, Wednesday is just a Saturday where you don't stay. Right? It practically is the weekend. Okay, so there we have. If you wanted to find out what the actual vertex was, if you want to find the coordinates, then that point is on your graph. Any points that are on your graph are on your original equation. Can you see here, I would like to plug -1/4 into my original equation. -1/4 squared is 1/16 times 2 is 1/8. Minus a quarter would be -8. Minus that would be -21. Maybe I did some mental math wrong, but that would be our vertex. I think that's right. So if you plug something into your original equation, you get points on your graph. If you plug something into your derivative, that tells you about slopes of tangents, and slopes of tangents will tell you where your graph is increasing and decreasing. So if we wanted to go and graph this now, we could go to -1/4, -21.125, and we would know that it increasing there, decreasing there, but you already know what a parabola looks like. If you wanted to provide some more scale, I would say this would be a really nice point to add. How did I find that point? I added 0 in for x. That would be my y-intercept. And that would give me -21. X-intercepts are nice to add, but if you wanted to find the x-intercepts, you'd have to factor, and if this one doesn't factor nicely, but it does, then you'd have to use your quadratic formula. Does it factor nicely? 2x and x, 3 and 7, make the 7 positive 3. Oh, yes, it does. Next graph. Do you remember graphing this one in grade 12 and how you would do it? Like, be hesitant, yes, if you showed me first. I like that. That's the confidence. I know exactly how to do this if you would show me. We're going to do it first with calculus. Okay? This is an x cubed graph. Maybe you remember what it looks like. We'll do a recap of grade 12 pre-calculus and how you would graph that after we're done the calculus. In calculus, you would say, find your derivative. That would give you 6x squared minus 6x minus 12. Good? Set your derivative equal to 0 to find your maximums and minimums. This factors nicely. First of all, I would suggest taking out the common factor of 6. So if we set our derivative equal to 0, we're making the slope of the tangent 0, meaning we have a horizontal slope. I'll probably say this a million times because that's the basic, this is helping you understand what calculus is doing. Right? If you just know the steps for doing it, then you're doing stuff without it making sense that tends to not turn out well in the long run for math. We always try to understand what's happening. So I find my derivative to find this is all the slopes. If I set my slope equal to 0, that's where it's flat. That's where I would have a maximum or minimum. I found out that they're at 2 and -1. So I draw a number line, I add -1, I add 2 on there, because those are the points where I would have maximums and minimums. At this moment, I don't know if -1 is a maximum or a minimum. I don't know if 2 is a maximum or minimum. But now, and beside this, I'm going to write derivative. If I plug in a number into my derivative, left of -1 if I plug in -2. And this is where I would say you don't have to actually mental math it all out. I would actually use the factored form. Can you see that if you plug in a -2, -2 minus -2 is a negative number. I'm going to change that color to blue. I agree. That would be negative. If I plug in -2 into this one, -2 plus 1 is negative. If you have 6 times a negative number times a negative number, can you see that this section will be positive? And if that section is positive, your graph is increasing. Next, if I plug something in between -1 and 2, like 0. 0 would still make this negative, but this second factor then would become positive. And 6 times a negative number times a positive number will be a negative number. This section will be decreased. 0 probably would have been really easy to plug into the unfactored one. Can you see that you would get -12? Still a negative number, still decreasing. But if I plug in something bigger than 2, like if I had to plug in 3 or 4 or 5, I'd be like, oh, I don't know if I want to do all that mental math in the unfactored part. But if I plug in 5 into the factored part, it's really easy to see that both factors are positive. Times a +6 is going to be positive. This section is going to look like this. And now I know that the following points, -1 comma something, that's going to be what we call a local max, and 2 comma something is going to become a local min. And our arrow diagram kind of tells us the shape of our graph. Can you see what the cubic one is going to flow like now? How do I find what those actual coordinates are? That's where they're points on my actual graph. This is where I would plug -1 into my original equation. -2 minus 3 is -4, plus 12, 8. Plug in 2, 16 minus 12 is 4, minus 24, -20. Did that quick. Possibility of mental math errors are apparent, could be in these questions, but for teaching purposes, it doesn't really matter. So, I have -1 comma 8. I will put 10 there and estimate -1 comma 8 to be there. That way, when I go my scale to -20, 1, 2, I can label 2 comma -20 that way. And what we have is we know that our graph has to be increasing to this point, decreasing in between, oh, I want to do that red, there we go, and increasing after. From grade 12 pre-calculus, did you remember that x-cubed graphs had n behaviors that were like lines? Because it's positive, it would have had to start down here, end up here. So our graph, sure enough, starts down there, ends up there. That was something from grade 12 pre-calculus, saying that's something you know about an x-cubed graph. That matches up from what we saw from calculus. In grade 12, you would have graphed this by finding all of your intercepts, x-intercepts and y-intercepts. The y-intercept is the easiest to find. You'd have found that by plugging in 0 for x, and you got 0 for y, so you would have had, fascinating that when I drew to scale, it worked out almost perfectly that it went through that point. You might have said, oh, maybe you knew that beforehand. No, it's just luck. Just pure luck that it matched up nicely. So we've got 0, 0. Next, you would have learned that to find your x-intercepts, you would have needed to factor. This one You don't have to use your factor theorem, remainder theorem, because it has a common factor of 0. So we can factor out the x, leaving us with 2x squared minus 3x minus 12. And then factor it again, if possible, 2x and x. To get 3 and 12, let's go. Does it factor nice? I write down the numbers. It might not factor nice. That's the only problem here. No, I'm not seeing the good factor thing right now. You could check with your quadratic formula, right? The b squared minus 4 times a times c. This is called the discriminant of your quadratic formula. A favorite thing on IB exams to see if you remember that from grade 11. The discriminant, which in this case happens to be 8 times this times 12 is 96 plus 9, 105. Isn't a perfect square, so that tells us that no, you couldn't factor this. You would have had to gone to your quadratic formula to find this point and this point. But if it was factorable and you did find those points, in grade 12, you then would have been able to graph this by saying, I know it starts down here, it goes through these 3 points, so this is how it has to match up, but you didn't know how high to draw it or how low to draw it, because you didn't know how to find the maximum and minimum. Calculus now solves that. Calculus finds that maximum and minimum. We can still use factoring to find our x-intercepts or the quadratic formula, but we'll get a much more accurate shape by just knowing the maximums and minimums. When you draw a smooth curve, like when I drew a smooth curve through that scale, I got my 0, 0 point almost perfectly just by trying to draw a nice curve through the points. So it gives us an even more accurate way of graphing. Okay. An x to the 4 graph. From grade 12 pre-calculus, you would say since it's positive and it's an even function, it's going to act like a parabola opening up. You would have to try to factor this with the factor theorem. Won't be nice. Probably won't work. And you would be stuck in grade 12 not knowing what it looks like. Now that we have calculus, we can find our derivative. 4x cubed minus 16x. Woo! So nice. Set it equal to 0. Notice you can factor out a common factor of 4x, leaving you with x squared minus 4, which is beautifully a difference of squares, which factors nicely to x plus 2 and x. That's a nice minus sign, extra thing. I don't like extra. It looks terrible. X minus 2, which tells us, split it up into 3. X could be 0, x could be negative 2, x could be 2. What have we done? We have found out that if we find the derivative, which finds all of our slopes, we set the slope to 0. Horizontal lines. Horizontal line will find all of our maximums and minimums. Factored it, solved, and we got 3 of them. We can now go to our number line. We can add negative 2, 0, and 2 to the number line. I'm going to label this as f prime of x. And again, take our green pen, plug in something less than negative 2, like negative 5. Can you see? This would be negative. This would be negative. This would be negative. A negative times a negative times a negative. This will be negative and decreasing. Without actually having to plug in negative 5 into here and do mental math. Next one, plug in something between -2 and 0, -1. This will still be negative. -1 plus 2, though, that would be positive. -1 minus 2, that would still be negative. A negative times a positive times a negative is positive. This part would be increasing. Between 0 and 2, plug in 1. 1 would now make this positive. 1 would keep that positive. 1 minus 2, this is still negative. This section will be negative, decreasing. And finally, something bigger than 2, like 8,000. This will be positive, this will be positive, this will be positive, meaning this section will be increasing. And so now we have where it's increasing and decreasing. We can look at our points. We know that we could plug in 0, comma something, -2, comma something, +2, comma something. The 0, I already know is going to be a local max because of how the diagram fits. The -2, a local min. The +2, also a local min. And if I want to find out where these points actually are on the graph, I'd have to plug into my original equation. So 0, really easy to get -3. -2 will be 16 minus 32. -16 minus 3, -19. And plugging in +2, because those are even exponents, will come out to the same thing. So if I was graphing here, I went -10, -20, 1, 2, 3, 1, 2, 3. I now know that I have the following points. I have at -2, -19, +2, -19, and 0, comma 3. I know that my graph has to be decreasing, then increasing, then decreasing, then increasing. And we graph a very accurate graph. The only thing we could have done in grade 12, pre-calculus, would have been possibly finding your x-intercepts, but this one doesn't factor nice, so it wouldn't have been possible with algebra. You could have found your y-intercept, but you wouldn't have known it was a maximum, and you would have known that the end behavior was like this. The rest would have been guesswork in between. We have now drawn something actually very accurate using calculus. A much better technique than the technique that we learned in grade 12. And the technique we learned in grade 12 only helped us with polynomials. This is going to help us with graphing logarithms, graphing sine graphs, cos graphs, any graphs that we want, we can use this technique for. Yeah, like this graph. Do you remember graphing these in grade 12? Again, I like that. Like, yeah, I'll remember once you show me. So we'll go through the grade 12 graphing of this. We will look at graphing in calculus as well. So if you found, let's see what we know from calculus first. You found your derivative here. Do you see that you have the quotient rule? We would keep the bottom the same, times the derivative of the top, minus keep the top the same, times the derivative of the bottom, over the bottom square. going to just factor this. Now, if I simplify this, f prime of x, I'm going to get on the top 2x squared, 2x cubed minus 2x minus 2x cubed plus 8x. Good? And if I simplify that on the top, that will just make 2x cubed go away. I'm going to get 6x over x squared minus 1 squared. So the calculus tells me if I set that equal to 0, the only place a fraction is equal to 0 is when your numerator is equal to 0. That can be seen because I can multiply both sides by the denominator right now, and I would just get 6x equals 0. So that tells me x is equal to 0. Now there are some things that are going to become important that we're going to find out in this unit. When we draw our number line, if we follow the same thing that we did in our previous example, the only point you put on here is 0, and you plug that into your derivative. But our question will also have another thing involved. You recognize in the original question that there are some non-permissible values, that x can't equal 1 and x can't equal -1. Those values will also get put as non-permissible values on your derivative chart. Because at those non-permissible values, and this is something you do have to know from previous years, that at those non-permissible values, we are going to have asymptotes. And when checking my derivative, I'm going to check what's happening less than -1. Okay? And there are some things in the equation that can provide us with shortcuts. First of all, can you see in the derivative here that the bottom is squared? When you square any number, it will be positive. So no matter what we put in the bottom, does it make sense that this bottom part is always positive? So now we're just looking at the top part. If I plug in something less than -1, would you agree that that would be negative? Decreasing. Between -1 and 0, still a negative number? Negative, decreasing. Between 0 and 1, positive, increasing. After 1, positive and increasing as well. So we now know that 0, comma something is going to be a local min. If I wanted to find the actual coordinates, I go to my original equation, and plugging in 0 would give me 0, 4. The other bit of information that you need to know from previous years for this question is that if x gets really, really big, you will have a horizontal asymptote. In fact, what you're doing is you're figuring out what is the limit as x goes to infinity. As x gets really, really big, does subtracting 4 really matter? Right? If Elon Musk loses $4, he just made a world record. Did you hear that? He has the world record for the person that has lost the most money in the least amount of time ever. Apparently he lost something like 185 billion in the last year. That's a lot of money to lose. Like you have to wear pockets with like holes in them all the time, and just like continually be putting money in your pocket and having it fall. Because his Tesla stock lost a lot of money. Okay? So I think he probably actually felt that. Maybe just to his ego, but I lost $185 billion. Ouch. Right? If he lost $4, probably okay. Probably not a big deal. If he lost $1 on the bottom, probably not a big deal. Probably can ignore it. In fact, that's what happens as x gets really, really big. You just look at the highest power, because that's the thing that affects it the most. Then you would have x squared over x squared, which is 1, which tells us we have a horizontal asymptote at y equals 1. And because the top factored so nicely, I know my x-intercepts are 2 and negative 2. Because if I plug in 0 for y, it's really easy to find out where that fraction is equal to 0, because the numerator would equal 0. Now, increasing and decreasing. Between negative 1, it is decreasing, so my graph would look like this. That's always decreasing. Then between negative 1 and 0, it's decreasing. And then increasing. And then increasing. So it's kind of interesting that we had decreasing, decreasing 2 times in a row, but there's actually a break in the graph. It still continues to decrease, but that asymptote switches where it has to be to make it decrease. And you get a very accurate graph of something that you would have graphed in grade 12. In grade 12, you would have done the same thing with your asymptotes. You would have found them. You would have found your x-intercepts here, here, and here, and then just drawn your graph towards the asymptotes as a result. And you would have found your y-intercept here, and since you'd already found all of your x-intercepts, and you knew it had to go towards your asymptotes, you knew it had to go up. But now we have actual reasons why it goes where it goes from the slope of the tangent. All right, we will do, what do we got? Couple more examples, 2 more examples, and we're done this section, so we'll get that done. F of x, 2x cubed minus 5. You know it's a cubic graph. You know that it's a positive cubic graph, that its end behavior would look like this. Now we're going to find out what this graph looks like exactly. Okay? If we use our derivative, we would get 6x squared. Setting that equal to 0 just gives us x equals 0. We have no non-permissible values. So on our number line, the only thing that we're going to plug in is 0. We're going to plug in values into our derivative. I hope you notice that your derivative is x squared. You plug in negative number squared, positive, positive number squared, positive. This is going to be positive here, increasing, positive here, increasing. It's kind of weird. Usually we had things switching, increasing, decreasing, increasing, decreasing. But 0 is an important point. That's really easy to find. 0, negative 5. Actually, I'm going to label it on that side. 0, negative 5. And if the graph is always increasing, how does this work? Well, first of all, if the derivative is equal to 0 at 0, negative 5, the derivative is 0, that means if we drew a tangent, that tangent would be flat. What happens on this graph to do that and this will make sense to you, but it always has to stay increasing. Can you see the only way that's possible is if it flattens out temporarily and then increases again. If it's increasing, it has to flatten out temporarily and then increase again. Now, going back to grade 12, this is an x cubed graph with transformations. You have a vertical stretch, you took your x cubed graph, stretched it by 2, translated it down 5 units. Some of you use lots of transformations for your IA, so now you're like, yeah, I remember that lots because I'm just finished writing about that. Thank you for bringing that up. Okay. So can you see that you have your x cubed move down 5? But now calculus is explaining why your x cubed graph has that little bend in it. Because it actually flattens out completely for a millisecond and then increases again. And an x cubed graph is one of the few places where you can have a tangent that goes straight through the graph at that point. And at 0, it does cut through the graph. Usually a tangent doesn't cut through a graph, it just touches it, and then sort of the graph bounces off the tangent line. But in this case, it cuts right through it. Beautiful. Oh, this is like all mathematics that you're like learned in pieces in different places. The calculus just sort of starts to bring things together and like, oh, that makes more sense now. That's why that shape was like that. Now you're known, it should flatten out at that point. So our last example, given the function, right, let's just up the level a little bit, ae to the kx plus 2. The y-intercept is at 0, 7. Does that match with your notes? Yes. Part of the graph is shown. We know that this point is 0, 7. Show that a has to be 5. Okay? Well, the only thing we know is the y-intercept. That's a point on my original graph, so that means when x is 0, y is 7. K times 0 would be 0. What is anything to the exponent of 0? 1. So now I could just go, this is 7 times a times 1 plus 2. So I solve that a is equal to 5. Okay? I think this is, part A is a good example of when you initially read a question, your brain probably says, I have no idea how to show a is 5. That might happen to you often when you see an IB question. Because they like to make problem-solving questions. Do this. I have no idea how to do that at all. Then, stage or part B of solving this question. Well, what the heck do I know? I know I have that equation. I know I have that point. So I guess I could plug in 0 for x and 7 for y. I don't know if this will help me, but I'll try it. That's a typical problem-solving way of solving. You probably don't know how to directly solve for something they're asking, but then you go to, what do I know? Does it help me? Sometimes you choose something you know that doesn't help you. And you check it for a while and you're like, that doesn't help. What else do I know? Maybe there's something else that will help you. Okay? And given that f of 10 is approximately 2.67, find the value of k. So now, what could I do? I could say that I know that when x is 10, y is 2.67. So I have a I already figured out is 10. E to the k times 10 plus 2. How would I go about solving this? I would probably use my calculator. I mean, you could use natural logs, okay? There's an algebraic way of solving this, but one thing you probably noticed on some of the questions on your take-home quiz is that there will be times that if you're allowed to use your calculator, it may be the fastest just to type this into y1 and this into y2 in your calculator and see where the two graphs intersect. So if I were to do that at this point, I could, like this one's not bad. You could get the e to the 10k by itself, take the natural log of both sides, bring it in front, solve for k. It algebraically wouldn't be too bad. I'd still have to use my calculator in the end to find k. How fast is it to use my calculator with my computer? Actually quite slow, apparently. But I would type this into y1, that into y2. And you will use this so much. Type it in right. And then second calculate, where do they intersect? Enter, 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 at x equals negative 0.2. Okay. I guess technically I'm rounding, so I should use my approximation sign and use 3 sig figs. K is approximately negative 2.00. Using your value of k, find the derivative. My derivative, how do we do the derivative of, you see it's a chain rule. Some things about e to the x that you're going to need to know. E to the x graph looks like this. As an asymptote here, all exponential functions. Y equals e to the x graph looks like this, with, of course, 0, 1, and 1, e. That's your e to the x graph. So what's going to happen to this graph of our derivative here, if we think about this as a derivative graph? We've got a vertical stretch, we've got a horizontal reflection. That would just flip it over. And it is not moved up or down at all. Can you see that your asymptote would stay at 0? So this graph is never 0. Okay, well, let's finish this one up later.